Hi everyone, Dr. Doherty here. I'm a nuclear physicist from Abilene Christian University. Today, we're going to talk about vectors. Okay, so what is a vector exactly? Well, it's a thing that's got both a length and a direction associated with it. So I'm going to say the force is 10 newtons pointing that way. Now the opposite of a vector is a scalar, which is just an ordinary boring number, like temperature or mass. So I can say it's 72 degrees, not at 72 degrees that way, because that really wouldn't make any sense. So the two examples that really help illustrate what vectors are to use vectors to show a position or a force, or maybe a field. So let me show you what I mean. So for position, all I've got to do now is draw an object somewhere, and a vector will point to that object. So to do that, though, I've got to specify a coordinate system. What are my x and y axes? Where is my origin? So then I can draw a vector from the origin to my object, and now I've got a vector showing the position. It's got a length, how far away I am from the origin, and it's got a direction. Where is it from the origin? Now later, if my object has moved to down here, I could draw a vector showing its position. I could also draw a vector going from the start to the finish, a displacement vector showing how my object has moved and which way it's gone. Vectors can also show forces. So if I take my object, I can say there's three forces that are acting on it. I've got something that's pulling it up and to the right, and something that's pulling it down. And vectors are a really good way to illustrate that. Now for the record, when you draw forces acting on an object, always, always, always draw the vectors leaving the object, even if it's a pushing force. So you always want to draw it like this, and never, ever, ever try to draw it like this. Otherwise, you're going to have a bad time. In more advanced ways, we can talk about vectors showing us a map of where things are pointing across a region of space. So I could show you where's the wind blowing everywhere in the country, or which direction does the electric field point across some region. I also learned in putting this video together that force vector is a line of shampoo. Now let's talk about trig. So I could define a right triangle. I've got some angle theta. The diagonal is called the hypotenuse. I've got the adjacent side from the angle, and I've got the opposite side. Now no one wants to spell hypotenuse every time, so let's just shorten that down a little bit. So I can use the trig functions to talk about how these things relate to each other. So you probably all remember SOHCAHTOA, the idea that the sine of my angle theta is the opposite over the hypotenuse, and so on and so forth. We also have the equation from our good friend Pythagoras that says that the lengths of these sides are related. So the hypotenuse squared is the opposite squared plus the adjacent side squared. So if I know the length of any two sides, I can use that equation to find the length of the third. Now let's use trig to talk about the components of a vector. So I'm going to draw a vector to get started, and it's going to go from the starting point down to the ending point. And let's say it's got a length of about 10 meters long. Well, this thing I can now treat like a right triangle, and I can give it x and y components. So let's go ahead and do that. So now I can treat this like a triangle by saying there's a x part and there's a y part. So how long is this? Well, I need to have some angle theta down here in the corner. Now the adjacent side to my angle, well, adjacent is touching my angle because adjacent means next to. I remember that cosine of theta is adjacent over hypotenuse. So if I know the hypotenuse and I want to find the adjacent side, I just solve for a. So I can say the length of this adjacent side, my x direction, is h times cosine of theta. Now similarly for my y-axis, well, sine of theta is opposite over hypotenuse. Now I'm on the side that's opposite from my angle theta, so I can calculate that the length of this opposite side is the hypotenuse times the sine of theta. So now I can figure out how long the x components and the y components are by plugging in that my hypotenuse h is 10 meters and my angle theta was about 37 degrees. And when I do that, I get that the length of the x component is about 8 meters and the length of the y component's about 6. And if we go and we draw a grid, we can see that that actually works out to be pretty good. Let's talk about how to add vectors together in a way that makes sense. So let's suppose I'm going to do two movements. My first movement is that I'm going to start over here, and I'm going to move 5 steps to the right. Then I'm going to move 5 more steps to the right. So that's my second movement vector. Well, now obviously, if I go 5 steps to the right and then 5 more steps to the right, I've gone 10 steps to the right. So we can see that graphically if I just grab this vector and I pick it up and I move it to the end of this one. And then the total length that I've gone is from the beginning of this vector all the way to the end of that one, which must be 10. So if I'm going to add two vectors together graphically, I just got to line them up head to tail and go from the very beginning to the very end, and that's the sum of my vectors. So now a more complicated example. I'm going to start somewhere, and I'm going to move 5 steps to the right. Then I'm going to move 5 steps up. Well, you might want to draw the vector like that, but that doesn't really help us and see how the motion worked or where we ended up in the end. So again, to add vectors, what I'm going to do instead is draw them from head to tail. So I've got my 5 steps to the right. I'm just going to pick up my second vector and drag it over here. And now I've gone 5 steps up. Then I can see my total distance from the start to the end is this pink vector. So I can add vectors graphically by just lining them up head to tail and see where the total puts me. That also works with forces. That's all you need to know. Now let's solve some problems. This year our freshmen in our Intro to Engineering and Physics class are designing and building mini golf holes. So I've got mini golf on the brain. Now let's think about how this is going to work. So let's take someone who's giving us 3 shots in their game of mini golf. The very first shot goes about 5 meters and it goes straight up, the north direction. Then they go around the corner, so the second shot has a length of about 6.52 meters. And this one's going to go off at a 40-degree angle to the northwest. So I'm going to write this as north of west. Then the third shot, they're really close to the hole, just a teeny tiny way to go, about 1.5 meters straight west. So now this has defined 3 vectors. To figure out where he ends up, I've got to add them together. So all good problems start with a diagram. Let's go ahead and draw this out. So here's our starting point down in the bottom corner. So vector number 1 is going to go straight up for 5 meters. Vector number 2, well, let's see. I'm going to draw a little horizontal and vertical line so we can be really careful about the angle here. I'm going to go a distance of 6.52 meters, and the angle here is 40 degrees. You've always got to be really careful about which angle you're talking about, or else you might get a really crazy answer. My orange marker from the floor says that putt number 3 is 1.5 meters to the west. So now I'm going to figure out how far he went from start to end by adding these 3 vectors together. And I'm going to show you the way to do that gets you the right answer every single time. That is to make a table of the x and y components. So putting all the bits together that we've learned so far. So all I got to do is make a table for putt 1, putt 2, and putt 3, and figure out what the x and y components are, and then we're done. Okay, so putt number 1. It goes straight up. Well, in my coordinate system, the x-axis is left and right, with the right being positive and left being negative. My y-axis, up is positive and down is negative. If my motion here for number 1 is straight up, that happened all in the positive y direction. So I know my x component is 0 and my y component must be 5. Now if I wanted to, by the way, I could throw in a little angle theta of 90 degrees, and I could have said that my x component goes as the cosine of 90 degrees, and my y goes as the sine of 90 degrees, but I can tell what the answer is without having to get my calculator out. Okay, now putt number 2 is the interesting one. So now I've got this triangle where I've got an x component and a y component, and we're going to use trig functions to see how they go. So here's my x component. This is the side that is adjacent to my angle, because adjacent means touching. So that must go as cosine. So now the length of that x component is 6.52 times the cosine of 40 degrees. Now this is my y component. This is opposite from my angle. So the length there must be 6.52 times the sine of 40 degrees. But you know without thinking much that if I've got a cosine here, I'm going to have a sine here. Now before we're done, we've got to be careful about direction. So this one is going to the left and up. If it goes to the left, the x-axis better be negative or I'm going to get the wrong answer. It's going up so y can stay positive. Okay, putt number 3. This is going to the left, so that must mean the negative x direction. So I can just write down the x component is negative 1.5 and the y component is 0. Now all we've done is use trig, treating all 3 of my vectors like right triangles, and found the x and y components using sine or cosine, or just by looking for cases of vertical and horizontal lines. The hard part is done. Now all I got to do to figure out the sum of these 3 vectors is just add things up. So the total x component is just this plus this plus this. So it turns out that negative 6.52 times the cosine of 40, as long as your calculator is in degrees mode, that works out to be about negative 5. So now my x total is negative 5 minus 1.5, negative 6.5. Now over here on the y's, I take 5 plus 6.52 sine of 40. That works to be about 9.2. So I know that from the start to the finish, I've gone 6.5 meters left and 9.2 meters up. If my diagram was drawn to scale, I can just look and see if these numbers make sense. See if maybe I got in radians mode instead of degrees mode, just by saying, does that distance seem reasonable? Now to finish the problem off, let's calculate the magnitude and the angle of my total length. Okay, so our good friend Pythagoras says that the magnitude of my sum vector is going to be the square root of negative 6.5 squared plus 9.2 squared. Now when I square this, that minus sign goes away, so I probably don't have to worry about that so much, but that works out to be about 11.3. Given the lengths that I've got here, to say that this is going to be 11.3 meters seems pretty reasonable. Now to find the angle of my vector, I find it easiest to use the tangent function. So you remember, tangent is opposite over adjacent. So if I have a triangle where my angle theta here, and this is x and this is y, that means that the tangent of theta is going to be y divided by x. And as long as the angle is off of my x-axis, that works every time. So then theta is just the inverse tangent of my y component divided by my x component. So in this case, 9.2 divided by negative 6.5. When I work that out, I get about 55 degrees. Now we need to be careful what we're talking about here. Because I defined it as y divided by x, this is an angle off of the x-axis. So this is my 55-degree angle, not this guy right up there. So that's the first example, the first real problem of adding 3 vectors together to be excellent at mini-golf. For example number 2, let's talk about the forces acting on a support in a bridge. If I take one of the junctions at this corner where I've got lots of I-beams that are meeting, let's find out how much total force is acting on that piece. So I'm going to take a little bit of a bridge support, and we can say maybe there's a force going to the left that's about 25 kilonewtons strong. And maybe there's one that's going down at a 45-degree angle. I've got that at about 40 kilonewtons. and then maybe straight down at about 50, and then down and to the right, a little smaller force of about 15 kilonewtons. So what I need to do is to add these four forces together. Now, can I add these graphically? You bet. All I got to do is now picture if I took all these vectors and lined them up head to tail. So maybe I could take this guy and bring it over here, and then I take this guy and bring it down, and I take this guy and bring it down, and I could see that maybe the sum looks like this, and I go down, and I go around, and I go down, maybe points to somewhere over there. So I would expect that the sum has a pretty big negative x component and a negative y component. But let's try to figure out what this looks like. So as always, I need to draw a table of the x and y components to get the right answer. So here we go. X component and y component. Let's maybe label my vectors. So I'll do 1, 2, 3, and 4 as I go around. So vector 1, 2, 3, and 4. And then we'll just total them up. OK. Vector number 1 points straight left. That's all in the negative x direction. X component's negative 25 kilonewtons, and I'm done. Y component is 0. Now, vector number 2, I've got an angle right here of 45 degrees. So when I figure out the x and y components, we're doing things based off of this angle. You always have to use the same thing. Now, if our angles are off of the x-axis, life becomes really easy because x is always cosine and y is always sine. Okay, so the x-axis is this length here. This is the side that's adjacent to my angle, so I'm going to use cosine. So I've got 40 times the cosine of 45 degrees, and it's going to the left, so it's negative. Now for the y component, I'm going to have 40 times the sine of 45 degrees, and it's pointing down, so that's also negative. Okay, vector number 3, 50 kilonewtons pointing straight down, really easy. Vector number 4, and again, I define an angle that points off of the x-axis, so that's my 45-degree angle right there. So vector number 4, going to be 15 times the cosine of 45 degrees. Now this one's going to the right, so it's positive. So having a table, I can go double check. Is number 2 pointing left? Yep. Is number 4 pointing right? Yep. We're good to go there. So my y component is going to be 15 times the sine of 45 degrees. It's pointing down, so that's still negative. Okay, the hard part's done. Now I just pick up my calculator and I add all the x's together, and then I add all the y's together. When I add the x's, I get a total length of about negative 64, and my total y's give me a length of about negative 89. So like we tried to guess by drawing, the sum of these four vectors, if I added them all up head to tail perfectly, would point somewhere way out about here. So the net force acting on this support points down and to the left. Well, how big is it in total? Okay, our good friend Pythagoras says the magnitude is the square root of x component squared plus the y component squared. And I can be lazy with the minus signs because those are going to go away when I square things. So I've got 64 squared and I've got 89 squared. We do the square root of that. That works out to be a magnitude of about 109 kilonewtons. The angle, so like before, we're going to do the inverse tangent of y over x. So when I plug in the inverse tangent of negative 89 over negative 64, that gives me an angle of about 54 degrees. But now I've got to be careful about what angle that is. So again, I've defined a triangle that has a hypotenuse like this. So then the angle I'm talking about is this angle right here, that theta below the x-axis. So that's 54 degrees below the negative x-axis. Always be careful about what angle you're looking at. Now, if you can do these two problems, you can do everything with adding vectors. All right, that's it for vectors. You're all experts now. Just remember to draw a really good picture. Think about the angles for your x and y components. Keep your calculator in the right mode, be it radians or degrees. Do the xy table, and if you do those steps, you cannot get the wrong answer. If you're in my class, thanks for watching. It's going to help your grade go up. If you're a random stranger on the internet, also glad that you're here. See you next time.